This is lecture from Module 6, Part 2. So, in terms of this module, the broken record, this stuff is important. You've got to grasp it in this module because we will do stoichiometry throughout the rest of the course. I would say it's the hardest part of the course, but it's not hard. It's hard if you make it hard. And I've had some students admit that later on, that they made it harder than it was. And what I mean by that is you allow the steps to confuse you and tick you off. When I get mad at stuff, I just, I can remember throwing my algebra book across the room when I was in high school because I didn't get stuff and it just was so frustrating. And when you're frustrated, my son reminded me last week, I play guitar for our little mini worship service that I do on video each week. And there's a chord that I hit all the time except that Saturday when we were recording. I couldn't get the chord. It kept messing up. And my son reminded me from his piano teacher that when you get frustrated about something, particularly if it's music, but it goes for anything, just walk away from it. Go away from it for a while because you're not going to get it, all right? So if that's the case for stoichiometry, go away from it for a little bit and then come back, and if you still don't get it, call me or email me. Or walk through the examples in terms of what you have. And because they're really good at explaining the steps. They go one by one, and if you read through those blue examples, I think you'll be okay. But as I say, this is important stuff. So I wanted to get it, and we've got a lot to do today too. Baby. Sorry, guys. Please work. Awkward. turtles have taken over my computer. It's just stunning how slow this thing is going right now. It's sort of there. Liam, can you hear me?
Yes, sir.
That's great. I'm so sorry about the delay.
No worries.
You haven't missed anything. Of course, I don't know. That's a big deal anyway. There you go. There we go. All right. If you're on page 171, that's what I wanted. Liam, page 171, please. Okay, so I introduced this last week. This is the first step. And what I suggested to you a moment ago is not hard, but it requires steps and it can become confusing. So we're going to try to take the confusion out of this deal. How about that for a cool, refreshing beverage stand? All right, a chemist wants to make ether. That's C4H10O. If you're following me, please do. And if you're not, please do. Example 6.3 on the bottom of page 170. The chemist uses, and I think we looked at this last week, but I want to just use it again. We looked at this equation and made sure it was balanced. You will need to learn to balance equations if you haven't already. And if you're still struggling with that, holler at me. Talk to me. I'm glad to help. So we determined that this was a balanced chemical equation last time. We counted all of the various elements on both sides and they were good. So if the chemist needs 134.9 moles of ether, what is the minimum number of moles of C2H6O and H2SO4 that he needs? So as we found out last time, you can compare any of the ingredients, in quotes, of a chemical equation, any of the reactants, and we're going to look again in a moment that the textbook separates it out, but you can do the same thing. If you look at the number of moles of a product, you can compare based on stoichiometry, based on the use of the factor label method. You can compare any of the ingredients in a chemical equation to one another and determine the number of moles needed in that chemical equation given the number of moles of any of the ingredients. And so, look at this question. In this one, they say they need 134.9 moles of ether. What is the minimum number of moles of C2H6O and H2SO4 that he needs? So in terms of this, you see that we're producing ether on the products side, and you need 134.9 moles of that stuff. So how much of the reactants, that's what they've asked for, the two reactants, do you need? Well, in order to determine this, you're going to first look at the balanced chemical equation, and you're going to look at the numbers to the left of each of the compounds. Those are the stoichiometric coefficients, remember? And or the number of moles, and or the number of molecules of that particular compound, right? That number stands for all of those different things. But in stoichiometry, it's the number of moles, and they are called stoichiometric coefficients. So, if you'll notice, we have in the balanced chemical equation 2 moles of the C2H6O producing, in terms of the chemical reaction, producing just 1 mole of that ether, and 1 mole of the H2SO4 producing 1 mole of that ether. In other words, based on the balanced chemical equation and the stoichiometric coefficients, you got 2 moles of C2H6O and 1 mole of H2SO4. Why do we have 1 mole? Because there's no number to the left of the H2SO4. Remember, it's 1 if there's no number. So, all we're going to do for this first step in what can be confusing, this is not confusing, it's just one step using the factor label method. So, you have been given the need for 134.9 moles of ether. So, that then goes over 1. Remember, in terms of our comparisons of units, you have to start with something, and it always goes over 1, right? So notice what we're talking about here on page 2, or page 172 of the example. So you got 134.9 moles of ether over 1, and now you begin the comparisons of what it is that you're trying to find. And the first one they do then is the first one in order, and that is the C2H6O, and they set up the equation like we learned in the first module to cancel what it is you're given in order to solve for what you're trying to find. And so that's what they do. You've got 1 mole of ether, and again, that's based on the balanced chemical equation, and that's being produced by 2 moles of the C2H6O, all right? And again, where did those 2 numbers come from? They came from the balanced chemical equation and the stoichiometric coefficients of each one. Well, look, the moles of ether cancel. And how do they cancel? Well, you're dividing one into the other, and so they become 1, right? And 1 times anything is whatever that is. And so you have 2 moles. After the moles of ether cancel, you do the math, and you're going to end up needing 269.8 moles of that C2H6O in order to produce the 134.9 moles of ether. And let's do the second one before I stop and see if you've got some questions. The second one is just as simple as it can be. And why is it simple? Because the number of moles is the same. Look, you've got 1 mole of H2SO4, that's sulfuric acid, I believe, and then 1 mole of the ether. And so all you're going to do is multiply, you notice again in the same setup of your factor label method, the ether cancels, you multiply 1 times 134.9, and so you immediately know that you'll need 134.9 moles of the H2SO4 in order to produce that 134.9 moles of ether. So, all we did was make sure our chemical equation was balanced. We remembered the stoichiometric coefficients of that balanced chemical equation, and we did a simple factor label method application to figure out the comparison of the 2. And that's really a good word to describe what we're doing. We're just comparing what we need in terms of reactants or products. In this case, they gave us, in terms of the question, they gave you product. Well, you can solve for reactants. You could solve for the other product, incidentally. Notice in this balanced chemical equation, you produced H4SO5, all right? Well, that was only 1 mole, so I can immediately tell you that the amount of moles that is produced in terms of that H4SO5 is also 134.9 moles. Why? Because of the stoichiometric coefficients. It's 1. All right? So tell me, is that confusing? Good. I'm not seeing, yes, sir.
I do have a question kind of sort of related, but how do chemists combine different...
Got to drop that. Thank you.
This is kind of unrelated, I guess, but how do chemists combine different chemicals and stuff? Like, for example, in this equation with the ether, how do they combine C2H6O and H2SO4? Do they just like throw them each in a chamber together and they automatically?
Sometimes. Most of the time it requires an energy source. You need to add some heat or something to that in order to get the chemical reaction going. Actually, that's a great question, and we're going to study that in terms of, it's called activation energy, and we'll get to that next semester. Excellent question. You know, you do good that way. Thank you. And all of you, in terms of your questions, they're always good questions, but thank you so much. Again, you guys have won the award hands down for questions. Most years, it's just the classic joke. What questions do I have? And I wish I could do a good cricket, but anyway. What do you say? This is important stuff, guys. You've got to get it. Don't be shy. If you're confused, then there's an excellent chance that somebody else is. You make sense? All right. Now, the next thing we're going to do is build on this. It's the second step. And that's what, I don't recommend the movie. It's okay on TV. But The Kingsman, I don't know if you ever saw that movie, The Kingsman. But in the movie, at some point in time, some of the bad guys' heads just literally explode into purple. Well, it's okay to watch on TV in some respects, but it's not a good movie to get to. But I digress. Where students' heads explode into purple comes with the next step. And so let's just launch into it. Well, it's actually, it looks like it's past, yeah, it's past Gay-Lussac's law. So let's do Gay-Lussac's law first. Turn to page 174. So all Gay-Lussac's law is relating the same concept that we just did with regards to stoichiometry to gases, all right? Would you write this down in terms of Gay-Lussac's law? I didn't fill it in for you. Gay-Lussac's law, it's on page 174, is this. The stoichiometric coefficients in a chemical equation relate the volumes of gases in the equation as well as the number of moles in the equation. And let's see. No, that goes to the next one. So, well, let's repeat what I just said, and then we'll speak to it. So, Gay-Lussac's law is the stoichiometric coefficients in a chemical equation relate the volumes of gases in the equation as well as the number of moles in the equation. All right? So, all that is speaking to is this. Let me write it up here. If I can just read it. I'm going to do something different than what's written in your textbook for a point of illustration. All right. Now, I mentioned to you early on that I wasn't interested in terms of help the boy, gas, liquid, solid. What's the word? It'll come to me in just a second, I hope. But anyway, I wasn't interested in, thank you, what is it?
Phase change?
Phases, thank you. I'm getting old. It's called sometimers. It's not Alzheimer's, it's sometimers. All right? So, I told you early on I wasn't interested in you tracking the phases in terms of chemical equations. Well, that just changed. But just for a moment, all right? So, Gay-Lussac's law says you can do the same thing with volumes of gases that you're doing with moles, all right, which is generally solids, can certainly be liquids, but what you're doing with moles, if you relate gas to gas. So, if we are given a number in terms of the oxygen, say, in terms of this oxygen gas, whatever number of liters we're given in oxygen, we can do the same thing we just did with stoichiometry and relate it to the carbon dioxide and to the CH18, whatever that is. So gaseous octane, there we go. So we could relate it to these two, all right, if we were given an amount of oxygen. If you're given, say, 100 liters of oxygen, how much octane do you need to produce in terms of this balanced chemical equation, and how much carbon dioxide, oh, that deadly, deadly gas, how much carbon dioxide will you produce? So you could relate that amount, 100, say 100 liters, all right, to either this one or that one. But you will notice, differing from your example, I have labeled this a liquid. So say you produced water in liquid form. You could not relate the oxygen gas to the water. It has to be the same phase, all right? If you are given moles, say 100 moles of oxygen, you could relate that to any of these as well. You could figure out how many moles carbon dioxide, water, and octane, but you can only relate gases to gases in a stoichiometric equation, all right? And I would prefer not to spend time going through that, because the main point is, if you're asked to do something with respect to gases in a chemical equation, you can only relate gas to gas in liter form. All right? Are we good with that? Do we need to spend a little time on that, or does that make sense? Yes, sir.
Can you use other volume units besides the liter?
Yes, but they need to be consistent. Right. We will use liters. So, and we're only going to use it once.
Why can't you do, like, I guess I understand why you can't mix two different phase changes, but why couldn't you do like solid and a solid and a liquid together?
Say it one more time.
Like, why does it have to be gas to gas only to use this law? Why couldn't you do solid to solid? Or
you can relate, because then we're talking about moles. In terms of mass, we're talking about moles. In Guy-Lussac's law, we're talking about volume. That's the difference. So, and specifically the volume of gases. That's what's unique about Guy-Lussac's law. Okay? Great question again. Excellent. Are you okay with that? Does it make sense? What I want you to know about Guy-Lussac's law: only relating gases to gases in volume form in a balanced chemical equation. Are we okay? Let's read through the rest of the notes there. So Guy-Lussac's law can be used in stoichiometry only if everything in the chemical equation is a gas. And that's not true. I just showed you it's possible that you could have something in a different phase. You just can't relate the gas that you're given to whatever is not in a gaseous form. If a problem gives the amount of the substance in grams, okay, this is the next statement and the harder part of where we're going. But is there any questions about Guy-Lussac's law? Is there any questions about that at all? Are we certain? All right, that's good, actually. If you have questions and you don't want to, you're a little shy about asking them, please holler at me. Please don't be upset and confused about this stuff. Again, I've been there, and it's frustrating when you don't know something and you feel like, there's no way to get answers about this stuff. And there is. If you'll text me or you'll call me, there's probably a good chance you won't get me, but you might, and I can talk then if I answer the phone or respond to the email. But if you don't get me, leave the message and I'll get back with you and I'll walk you through this stuff. It's not hard. It's really not hard. All right? Which a lot of you in your tests are showing. I mean, you're getting this stuff. So again, I don't mean to accuse if you're doing fine, but if you need some help, that's what I want to do for you. All right, so mass relationships in equations. And this is the next step that I've suggested to you causes heads to blow. All right? And I'm reading from your notes. If a problem gives the amount of a substance in grams, all right? And we are going, just had the excellent question, does it have to be liters? Well, in this instance, it has to be grams. So if you're given an amount of substance in kilograms, you're going to have to change that to grams, all right? And I'll show you why in a moment. But for now, if you're given an amount of substance in grams, not in moles, all right? Because the stoichiometric coefficients tell you about moles. And we solved that fairly simply. It was one step. It was relating the number of moles that they gave you to the stoichiometric coefficients in your equation, doing a little bit of simple math, and you got it. Well, this is an extra step. It's all it is, an extra step, and it's not hard, so again, stay with me. If the problem gives you the amount in grams, you must first convert grams to moles in order to do stoichiometry. The units are different, all right? Moles are not grams, but they can easily be converted. Grams can easily be converted to moles, and vice versa. All right? And we'll do that in just a second. Using the chemical formula, and, oh, here we come, it's the periodic table time. Oh, boy, I wanted to get back to the periodic table. Using the periodic table, calculate the mass of a known single molecule. And this number of AMUs, as you remember, is also the number of grams of the molecule that it takes to make one of those molecules. All right? So I'm reading the notes and then we're going to walk through it. Once the number of moles has been calculated, use the conversion relationship, again, the factor label method, between this number of moles and any other of the molecule's number of moles in the chemical equation. We just did that. We just learned to do that. That was our first step. Well, we're doing the first step as a second step now, all right? Then use the number of moles times the number of grams in 1 mole of the other molecule to determine the number of grams. So that's probably as clear as mud, but let's walk it through and show you that it's really, really not. It's steps. Page 177 is a great example. If you will follow the steps in there, you can do it with everything you've got because the principles are the same. You can relate anything in this equation. Let's get rid of gases. All right. You can relate anything in this equation based on grams. All right. And then convert it to moles. All right. Compare moles to moles. And then go back to grams. Before we even do this, I love the pictures, so turn over to page 179. There's a pretty picture for you. So if you ever get confused, if you're ever pulling out, see, I'm warning you, don't be confused by stuff and let it get to you. Oh! So the moles of a chemical. Look at how you got to moles. You had grams of one chemical, you go to moles. You compare moles to moles, which is our first step this morning. We did it last week too, but our first step this morning. Then you convert moles back to grams. Look at the top. They've got red X's. You can't go from grams to grams. You can't do a simple factor label method to compare grams to grams. It can't work that way. If you try to do it that way, you're going to get it wrong. All right? So there's our steps. That's what we're doing. We're starting with grams, we're converting to moles, we're comparing moles to moles, we're converting back to grams. All right? So here we go. 177 at the top. A chemist needs to produce 100 grams of gallium chloride using the following reaction. 2 moles of gallium, or 2 gallium element, 2 atoms of gallium, or 2 molecules of gallium, plus 6 moles of hydrochloric acid produce 2 moles of gallium chloride and 3 moles of hydrogen, which of course is a diatomic. Just for old time's sake, let's hark back to our youth. Let's go way back, three modules ago, and let's see if this thing is balanced. We know it's balanced because they already gave it to us. But there's 2 gallium on the reactant side. Let's see, 1, 2 on the product side. And then there's 6 hydrogen on the reactant side. Let's count them up. 3 times 2 is 6. That works. And there's 6 chlorine on the reactant side. 2 times 3 is 6. So voila, we've got a balanced chemical equation. We're going to revisit it just to remind you. So there's our chemical equation. We're trying to produce gallium chloride using this following reaction. How many grams of gallium and hydrochloric acid are necessary to accomplish this? Well, you're starting with 100 grams of gallium chloride. So the first thing you're going to do, they gave you grams, so you're going to go to your handy dandy periodic table. Take it out for me, would you? And because I want you to track this. All right? There you're going to your handy dandy periodic table, and you're going to start to searching, and if you want help, here on your second periodic table is the names to that stuff. But there I see Ga, gallium number 31, all right, and look what's below it, 69.7. So in terms of the number of grams for 1 mole of gallium, we write that down, 69.7. And then we start searching again, searching, scanning. Right there at number 17 is chlorine, 35.5 grams in 1 mole of chlorine, but you've got 3 of those things in gallium chloride, so you're going to multiply 3 times 35.5 and add that then to the 69.7. Go back again. 69.7 in gallium, and what you have, voila, is the number of grams in 1 mole of that stuff in that gallium chloride. All right, and look at there. They did the math for you. 176.2. Well, they say AMUs, but of course we know where they're going with this. 1 mole of gallium chloride then is 176.2 grams. I'll stop there. Is there questions how we got that? So, whatever they give you in grams, you start by looking at your periodic table, you add up what you've got, whatever the molecular formula is of whatever they gave you, you add up the number of grams per mole, and then you have how many grams in 1 mole of that stuff. All right? And that's how we started step 1 this morning, right? That's what they gave us. They gave us the number of moles in terms of this thing. Excuse me, you have the number of grams in this 1 mole of stuff. Well, they gave us 100 grams of that gallium chloride, and now we want to figure out the number of moles. I misstated in terms of saying the 176.2 was moles. Of course it's not, it's grams. But we started out at 100 grams of that stuff. Now we want to find out how many moles of that same stuff that we have. Well, we're going to set it up such that the grams of gallium chloride cancel. And again, what is that step in the middle of page 177? It is simply comparing via our factor label method what they gave you, 100 grams, to what we just figured out, how many grams in 1 mole. And so we do the little bit of math, you divide the 100, in this case by 176.2, and so what you figure you've got is 0.5675 moles of gallium chloride. All right? So now you've arrived at what we started with in step 1. So I apologize, I got ahead of myself just a second ago. So now you've got what we had in step 1. So this step we've already been through. You're going to compare what you've got with a factor label method set up to the number of moles in the balanced chemical equation. And in this case, they're asking for the gallium and the hydrochloric acid, the reactants. And so in this instance, we see that 2 moles of gallium will produce that 2 moles of gallium chloride, but it takes 6 moles of the hydrochloric acid to do the same thing. So in this instance, look how they set it up down here. They showed what I just told you, 2 moles of gallium produce 2 moles of gallium chloride, 6 moles of hydrochloric acid produce the 2 moles of gallium chloride. Then they set it up with factor label method. In the step 1 that we started with this morning, they put the moles that were started with this morning earlier, but what we just solved for over that equation, comparing the stoichiometric coefficients 2/2 in terms of gallium. Do the math, and of course 2 into 2 is 1, and so you know you've got 0.5675 moles of gallium. There's a difference though with regards to the hydrochloric acid because you've got 6 moles of it versus the 2. So in this instance, the 2 divides into 6, you're going to multiply the 0.5675 times 3, and you end up with 1.703 moles of hydrochloric acid. Let me stop there. Is there any questions about step 2? Step 2 is what we started with this morning. That was step 1. We added a new step 1, which was converting grams to moles. And how did we do that? We looked at the number of grams in 1 mole of the substance that they gave us, and then related that to the number of grams that they gave us in the question. All right? Are we okay? You sure? Are you sure? All right. Well, why is it that I'm about to glaze over? Turn over to the next page. It's the last step. And oh, we have our picture to remind us it's the last step. So we figured out the grams of one chemical, we converted it to moles, we compared to the moles, we produced the moles in the last step on page 1. Now we're going back to grams. So you got moles, but in order to find grams, you're going to have to do the same thing you started with to begin with in this thing, and that is you got to find the number of grams in a mole of what it is that they're asking you for. And so that's what they did in terms of the gallium. Well, that's pretty simple. It's 69.7. So a mole of gallium is 69.7 grams. And so in terms of what we solved for, we actually have in terms of our in terms of this equation, we started with 100 grams, we converted of gallium chloride, we converted that to moles, we compared moles to moles in this chemical equation, so we found out we have 0.5675 moles of the gallium. We just found out that there's 69.7 grams in 1 mole of gallium. So now the final step is to do the factor label method to figure out exactly how many grams we have, which is, in terms of what we just solved for, 0.5675 moles of gallium. And look at the moles of gallium cancel. You have 1 mole, there's 69.7 grams in 1 mole of gallium. You do a little bit of math, and so what you end up with then is 100 grams of gallium chloride needs 39.6 grams of gallium in a balanced chemical equation. All right, we'll do the same math for the hydrochloric acid. HCl, hydrogen is 1.01, chlorine is 35.5, that's simple math, 36.5. So a mole of of hydrochloric acid is 36.5 grams. You do the simple factor label method, so moles of hydrochloric acid cancel, and you can solve for grams, multiplying the 17 at 1.703. Again, that's the number that you solve for, comparing moles of gallium chloride to moles of hydrochloric acid, and do the little bit of math, and you end up with 62.2 grams. So if you want to produce 100 grams of gallium chloride, you got to start with 62.2 grams of hydrochloric acid. Yes, sir.
So if you actually went into a lab and got 39.6 grams of gallium and 62.2 grams of hydrochloric acid and combined them, you would actually get 100 grams of gallium chloride, right?
Right on the button.
So they're actual, like, physical amounts. They're no longer just like random numbers floating.
Which is precisely why it's done this way. So a number of moles, remember I told you, as we used moles because it was something we could deal with. We couldn't deal with AMUs, they're way too little. So moles, though, is something we can relate to. Grams, even more so. So that is a weight measure, it's a mass measure, but we can relate directly to grams. So yes, give and take, inefficiency of a chemical equation. So yes, what was the numbers again? If you take 62.2 grams of hydrochloric acid and 36.5 grams of, no, that was the hydrochloric acid. Where did we go? So yeah, 39.6 grams of gallium, you should be able to produce right about 100 grams of gallium chloride. I probably wouldn't, I'd mess it up. Good question. What do you think about that stuff? We got a little more to do, and it's the end of class. We need to do empirical formula, and maybe we will. Maybe I'll just introduce it to you fast, and then I'll go back over it for you a little bit next week when I hand you your test to take home. Look at the definitions of, and you'll fill them in here on the back. So in terms of molecular formula and empirical formula, they're on page 186. I'll go over this a little more for you next time, just in terms of, because we're having to rush. I'm going to need your exams. I've got tons of stuff to turn back to you. And I need to do that. Man. Time doesn't fly. It's just hard when you're trying to set up in here and get computers to work and all that stuff. Well, molecular formula is this: the chemical formula that provides the number of each type of atom in a molecule. All right? Molecular formula simply tells you how many of each atom is in a molecule. So water, there's 2 atoms of hydrogen and there's 1 atom of oxygen. That's the molecular formula. The empirical formula, though, is the formula that tells you a simple whole number ratio for the atoms in a molecule. So sometimes the molecular formula, I'll have to take more time with this. Let me just run through examples real fast, just to sort of introduce it to you, and then I'll say a few things more about it. Look at example 6.9. So the molecular formula of 3 compounds are listed below. Determine the empirical formula of each compound. So C4H12, all right, that is a compound. I can't remember what. But that is the empirical formula in terms, well, they say the molecular formula, that's right. The empirical formula, can you break that down into something in terms of least common multiples? Well, yes, you can. You can break that down to CH3. You can divide everything by 4 and get CH3, right? Same thing with, I can't remember what that is either, Na2S2O8. Can you break that down? Well, as a matter of fact, you can. You can divide by 2 and you can get NaSO4. All right? Look at the last one, K2Cr2O7. Can you break that down any further? As it turns out, no you can't. So nothing goes into all of those numbers. So as it turns out, K2Cr07 is already an empirical formula. And I will talk more about these things next week. There's not a whole lot I want you to know about it other than that simple math and least common multiples. But I know I just rushed it, so I'll speak to it just a little bit more next week.